All right, folks, now we're ready to do part B, where we investigate standing sound waves and use the resonance frequencies of a tube of known length to also determine the speed of sound. Okay, let's take a look at that. Okay, the apparatus for part B looks just like the apparatus we used in the first part of the experiment. Only now we're going to create standing sound waves instead of pulses of sound that travel through the system. So let's see how we do that. The main change is that now we're going to use our function generator to generate a sinusoidal voltage of a frequency that we control. And now the frequencies will be in the range of hundreds of hertz. Okay? Once again, the signal from the function generator is amplified and passed to a speaker, generating now a sinusoidal sound wave. Okay? The sound wave propagates through our tube, and then at the end of the tube, it's reflected off the back of the tube, which is closed. Okay? As a result, we get something that looks like the following. We have our initial wave with a particular amplitude and frequency that's traveling to the right, and then we'll have the reflected wave, which will have the same frequency and approximately the same amplitude traveling to the left. When these add together, they produce a standing wave, as we saw in the demonstration a couple minutes ago. Algebraically, we can see it here as well. The total wave, which is the sum of the right and the left moving waves, works out to be this, a standing wave, where the dependence on position and the dependence on time are separated. Okay. Now, as you know, for standing waves that have, in a system that has boundaries at both ends, the wavelengths that can fit into that system are restricted. We only have certain resonance frequencies or resonance wavelengths. For example, in the classic example of a wave on a string that has two fixed ends, we all know that this system can support only certain types of waves. This wave that has a node at the beginning and a node at the end. This one here that has a node on either end and an additional node in the middle. This one here, and so on. The equation for a standing wave in a one-dimensional system that has either two fixed ends or two free ends is the following. The wavelength must be 2L over n, where n is an integer, which can take on values 1, 2, 3, and so on. Those are the only possible standing waves that will fit in this system, certain resonance wavelengths. And then, since we know that lambda times f is equal to v, we can convert this into an equation for the frequency. And the result is that the frequency is also quantized. The frequency must be, of a standing wave, must be v over 2L times n, where n is 1, 2, 3, and so on. I said quantized there, and I meant it. We're going to see that the same thing that produces quantization of frequencies, of sound frequencies in a standing wave, the same general phenomenon, produces discrete energy levels in atoms. Because those systems are also standing waves, only now they're going to be standing matter waves. Well, that's just some foreshadowing. I want you to see how this is, this material is connected to the material for our course. Okay? So how are we going to do the experiment again? Let me just go back to the top. I'll say another word about that while we're here at this point, and then we'll go on. So in order to do this, what we're going to do is place the microphone at some position in the tube and leave it there for the first part. For example, you might put it here at the end of the tube. Okay? Oops. Sorry, the microphone hangs from the top. you might put it here at the end of the tube or at the beginning of the tube. Either way, it doesn't matter. Then I'll have you vary the frequency of the sound being produced by the function generator. And what we'll find is that in general, the amplitude of the sound at the microphone will be small, because if we're not at the correct frequency, we can't efficiently couple sound energy into the tube. However, when we get to one of those special frequencies, the resonance frequencies, then we can efficiently couple the sound waves into the tube, and we'll build up a sound wave of high amplitude in the tube. Actually, let me erase that. And so we'll get a big signal from the microphone. So what you're going to do in the second part is to measure the resonance frequencies. And you'll do this by slowly varying the frequency from the function generator, excuse me, there we are, until you see resonances, and then picking out the first, second, third, fourth, and so on, resonance up to the 8th resonance. It's pretty quick, you'll see. I'm going to have you do one more thing after you measure the resonance frequencies. And this is really to make a connection to the second part of the course. This system allows us to do more than just measure resonance frequencies. We can also map out the wave function of the standing waves. To do that, we'll set the frequency equal to one of the resonance frequencies, maybe the first or the second or the third resonance frequency. And then we'll do a set of measurements at that fixed frequency. We'll do measurements at different microphone positions throughout the entire tube, from the beginning to the end. Maybe we'll start at a position that's 5 centimeters away from the left end. And then we'll go to 10 centimeters, 15 centimeters, and so on until we get to the other end of the tube. And at each point, we'll record the sound amplitude, okay? By doing that, we'll be able to map out the amplitude of the sound wave as a function of position in the tube. So we'll get a map of the wave function, okay? And we'll talk a little bit more about that when we get to that point. But that's kind of fun too. All right, well, that's all I wanted to talk about right now. So now we'll take a look at the experiment for this part of the lab, okay?